So this part is dedicated to Europe. So I originally, when I was doing my PhD, I was working on the persistence of intermittency side. And then after work with Europe, we go to the persistencies of equilibrium integrals. So today I'm presenting some work on this kind of idea of absolute equilibrium in a kinetic system, which is gyrokinetics, where the plasma has a background magnetic field. And I have a collaborator in Tokyo, in Nice, Japan, and in our university, USDC in Tufri. So I will talk both gyrokinetics and fluid, but most emphasis will be on gyrokinetics. So I got many questions. Where is USDC? Okay, so USDC is here, and the NIPS is here. And actually, okay, question is answered. Okay, so I will talk, as I said, I will talk about mostly on gyrokinetic absolute equilibrium. So I have several versions of absolute equilibrium. In Euler, people have done in Fourier space, and I remember Montgomery did that with some other bases. I will also do it in Hankel space or Bessel space. Okay? And I will present some preliminary numerical results performed in NIFs here. So microcalculators. And also to free the analytical calculation is also preliminary results. As I said, most time will be here. Some of the work and the results are still underway. I'm working on it. And due to time limit, working time or presenting time, okay, so why should I talk about gyrokinetic absolute equilibrium, GKAE? Okay, so magnetite plasma is highly complicated with motion reactive structure. Gyrokinetics in the rich physics was very challenging for theoretical and numerical approaches. So, we have successful experience of explaining to understand real turbulence. And gyrokinetics is useful and less explored. The first nonlinear gyrokinetic distribution was invented in 1981, so it's kind of a new thing. So the idea is that it's hard to solve the system directly, so we try to find some relevant things. So one of the relevant things is some equilibrium of some special treatment of the system. Yes, it's again the idea. So turbulence is so difficult, so we find something something relevant. The idea is the persistence of the absolute in the turbulence. And not to mention that the absolute equilibrium itself is interesting, also the relaxation process is interesting. So we should try to find something. And also this is relevant to the low self-organization in two dimensions especially. Because sometimes it's exactly the inertial scaling as gamma and the U is now working on actually in some cases quite relevant. Okay, so the idea is that turbulence is a mixture of very non-equilibrium statistics and equilibrium statistics. So the idea is this is one side is equilibrium, the other side is quite non-equilibrium. This is non-equilibrium equilibrium, and there are pioneers already in this way to bridging this kind of extreme cases of statistical mechanics to understand turbulence. So turbulence kind of mixture to we see this morning is this Chinese philosophy, old philosopher Tai Chi. It's not black and white. We have the nature of both. So I remember the lawyer have a picture about the universe. We have some double finished picture. So here is actually the Scandinavia picture I found on the internet, saying that we have some picture here. I didn't quite understand what that's what I mean. So actually another remark. I originally thought that the strategy were taught before me on tigers. So I don't have much materials on what is galactic intrication, so I will briefly mention that here. So this was introduced by TDB. The idea is that he do the Fourier transform for all the equations, also using MHD, and he only keep part of it, and then he found that this system satisfies the Liouville system. Liouville system in the following sense. So Liouville system, UK dot is time derivative. You need to sum of alpha, so suppose UK alpha I vectors. So it's alpha plus partial beta equals 0. So this is what I mean by the Liouville system here. And here I is for the 3 dimension XYZ. Okay, so and then he knows at that time he only knew that the conserved quantity is energy. Actually, now we know that this is for driving. And then he concluded the energy equipartition. Now we know that if you helicity, the equipartition is not some kind of combination of energy and helicity. And in the 2D case is energy and the entropy. So we practice this idea to gyrokinetic system. So what is gyrokinetic? I'm not sure whether also pass. I'm not in this field, so I will introduce a little bit on this. So the starting point for gyrokinetic is the Vlasov equation as presented by Royal this morning on cosmology, similar to that. So this is the plasma velocity distribution function. It's a function of space that's here and the velocity. And for the n plus Maxwell equation, or if we are doing simplified case, the Poisson equations for electric potential. So we have Vlasov, Maxwell, Poisson equation. So the idea here is that in plasma with strong background magnetic field, we know how the particle is moving. So unlike Navier-Stokes or the other systems where we don't know much details of this kind of thing, for example, in Navier-Stokes, we don't know how to do subgrid modeling because we don't know what the ensemble is, or we don't know the detailed dynamics. Here, the particle is moving very fast along the magnetic field, so you can introduce some very accurate asymptotic expansion so that you can closely it's cutting higher order terms. It's called the gyrokinetic system. So here I just have one line introduction because in general people, for example, when I was in Princeton, I talked to the pioneer of this gyrokinetic simulation, really, he gave me a paper, had one paragraph and several lines of equations. And then I read it, I found that, okay, this is a subgrid model for turbulence. So why we say that? This is the space, we can write the gyro average, so-called the internally average over the angle, but actually we can write the angle average as a spatial average. We only need to introduce two delta functions as the kernel of the integral. So for any function phi r, for example, the velocity or anything else, we first fix the average is spatial average to this plane perpendicular to the magnetic field, as shown this here. So we introduce this delta function. And again, we average over this ring by fixing the length to the gyro center, the point, the particle position is here, and this is called the gyro center. The distance between this is fixed by this, the second delta function. So we divide by the weight, which is the length of this ring. So this average. for PDF, so for mathematical convenience, the equation can be either of f or h or g as you do some transformation. For here, we use the g, which is the non-adiabatic part of the fluctuation of the PDF. So, because it introduced some mathematical elegance, so that we can treat it easily. So in G, the equation looks this way. In 3D, we can then practice the paradigm by TDD for this kind of system. In this talk, I will only talk about the 2D gyrokinetic instead of the general 3D case with that one. Okay. So the first version of the gyrokinetic absolute equilibrium. We write the equation in x is the configuration space coordinate and the velocity space. It looks like this. As I said, I push 2D, so this term is integrated out on candidate is 0. Okay, so 2D, we have the invariance. It's very interesting that we have a continuum invariance. For any velocity, this guy is conserved, g squared of v. And we also have the kind of energy. The energy is the electrostatic energy rated by this kind of response function. And the system is closed by this quasi-neutrality condition. We have the brackets with R here is with gyro average. So this phi is the electrostatic potential. So this system is closed. This system describes how the guiding center is moving in this space and velocity space, configuration and velocity space. Okay, so we do as TDV did on the Fourier transform the equation when we write these. Remember that we have the J0 here, which is the Hankel transform as presented by the former speaker. I'm sorry. The quasi-neutrality condition comes here. This J0 is the first zeroth order Bessel function, which comes from the gyro average. You can remember that when we average, we have exponential function. So we have a theta there, we average, effectively we average over the angle, so that as the former speaker showed the formula, it's a Hankel transform. So we can prove or show that the Fourier system, Xiaolong holds for this system. And we have a quadratic invariance, which are logic. We can prove this. So we can find that the canonical equilibrium distribution will be looked like this. But here, the interesting thing is that we have 1 plus a continuum control quantity, which is actually kind of non-trivial thing here. So we need some special technique to solve it. This is the canonical equilibrium is the Gaussian distribution for function weight instead of for finite number of variables. So we write it in this way. Then we need to introduce some technique to make it work. First, as I see here, this is a function of v. To write it in a generalized Gaussian distribution function, we need to extend this variable into 2D integral. So we introduce the C here. We need to introduce the delta function to extend this integral into 2-dimensional integral u and v. Then you will write it this way. And then this is called the covariance function, inverse of the covariance function. Then we need to do the functional inverse to find the covariance function. Because we are doing a continuum of variables instead of finite, so this is not a matrix, it's a function u and v. So we see that we still have to keep this delta function, which came from here, originally introduced here. So, okay, then from here we can calculate everything whenever we want. Okay, so here is some remarks on the results and the subtleties. Then let's look at what is the energy spectrum of G as we introduce this guy. In 1D, we need to remember, as I said, this is a 2D distribution. We need to come back to 1D. So it should be 1 over R. But the function is simply here. Why? This is the details. Actually, it's intuitively direct, but we will need to do it, introduce some mathematics to work it out exactly. Actually, even my collaborator have difficulty to understand it, so we have somehow separated each kind of thought. Anyway, so the idea is that if we are concerned about 2D covariance. So what exactly it is? If we write this way, introduce an infinitesimal, we find that this guy is equal to this guy. Okay. So in the 1D case, it's just 1 over R, the density. This is trivial thing. And if you like, you can write in an integral way. Again, you'll find that the integral over 2D reduced to integral over 1D, the kernel becomes 1 over R. So again, it shows that the 1D distribution function is 1 over R. So if we want to go to the some more details up to this. G wave was introduced as a 1D density in S. This is the constant motion. Then the prescription of discretization in numerical calculation or even analytical calculation we did earlier should be the following. And one should not use Gi equals G I of I or actually Vi squared. So we should not be scared by the function. In 1D is very regular thing. Okay, then in numerical calculation, we cannot work on the continuum thing. We need to discretize the system. So this is the discretization. GK system can be discretized from the beginning. Suppose we don't, in a numerical calculation, we discretize the system in one code. Right? So analytically, we can also start to discretize the system and do the, just as the TD, we have finite space, however large it is. So we can calculate a split equilibrium. And we can also discretize the result from the previous slides. And with the prescription given here, delta ij over mij equals delta u. It goes to back and forth with delta u minus v. You get the consistent result. And everything's fine. It's interesting that LFV said that this guy should not appear. Actually, I did not realize that people could have this kind of problem. The issue is the following. G of K Vi now is not the exact solution to the original continuum system. Once you discretize, it's some kind of approximation. It's trivial thing in numerical analysis. Everybody knows that. But we should keep it in mind. So it's not surprising that we have a correction term, right? What is exactly the formula of the correction? It's just numerical error, something like that. What is the numerical error here? It should be defined by the absolute distribution function started from the discretized system. So this should not be surprising. Yeah, I forgot to. Yeah, this is what I just said. Contributes an extra term for discretized 1D distribution. Cij, should write it in this way. So, it's Cii. I was supposed to be yes. I missed something, sorry. Yeah. some mistake here. Yeah, 1D distribution multiplied by delta V. So I don't need to write the details. Okay, so this is the first version or the first two versions, continuous version or and the discretized version. Then we do the numerical calculation. So first we check the conservation property. As I said, g of any velocity is conserved. We have two energy and complement of V, but numerically we have to discretize it. So we have this very nicely checked this kind of conserved quantity, energy and velocity. And the numerical simulation, we do a modular resolution, 64 moles, and we have initial pumping here. So the K equals K0 equals 3, as I remember. So this is the initial growth of the other moles, and this is the damping, not damping, the relaxation, because I don't have dispersion of the initial two moles. K0 and K02 here, X and Y. So finally, the system goes to steady state, equilibrium state. So this is the result by analytical calculation from discretized dissipation. And this is the numerical calculation shown here. For a negative temperature state, we see that we have energy peak at the low moles and it's lower at the high moles. And the numerical calculation here is this. And initially, the system starts with this. So we have this. And further, we check this formula. Check this formula because it's interesting that, as I said, Gk of V is 1 over alpha is equipartial energy. So for 2D, the energy spectrum sum over the share of K will be proportional to K. So you peak at the high K. But if we have negative alpha 0, as the denominator goes to 0, we have the opportunity of energy goes to low modes actually, even for this discretized system. This is the effect of discretization or quantization. So actually it's confirmed by numerical. Look at this figure. For any V, as K goes, we see that energy really goes to low modes, and it's lower at high modes. It's a confirmation of the second correction term. Okay, so I have do some calculation for. In the previous version, I did not touch any velocity. Now I want to do similar things for the velocity variable. So here is the Hankel transform for some reason, because general average is the angle symmetry. We have the the Hankel transform is appropriate. So we have these two conserved quantities now in this program because we integrate over velocity. So doing the same game, we can get the energy spectrum in this way. So we have two conserved quantities. So this is some details. Usually, I can do mathematical game if you like to discretize B, but I don't find any use of this so far. So I said use this. I hope you can find some use for it. And we can, if velocity is bounded, so we should use the Fourier Bessel series, and the similar games can carry it over, and we can calculate. But they look similar, but now we have some dirty things because of the series. The orthogonal property somewhere I did not show here. We need to work with the first order Bessel function. In the continuous case, all these guys becomes B here. So, okay, this is a numerical calculation. I don't think I have enough time, so I will skip this. Anyway, I want to say here is that we somehow confirm the calculation. Look at this formula. This is symmetrical about K and Z, or K and D. So numerical calculation, previously they don't have a calculation, theoretical calculation. They don't know what they should plot. Now I tell them that what you should plot is something like this. Originally they plot this, or earlier papers they plot some other things. So this kind of confirming our calculation. Okay, so I promised I will talk about two-field, but I don't have time anyway. I finished part of it. Thank you.
I have just one remark and one question.
Yeah.
The remark is you can define absolute equilibrium for non-quadratic Hamiltonians. This can be done, for instance, for a compressible flow, or it can be done in the case of the Gross-Witkowski equation for fluids, in which case you get just a standard segment-order phase transition as an absolute equilibrium. So my question is here, why is it always quadratic? Your Hamiltonian, don't you have compressibility effect?
No, because the velocity is E cross gyro angle E cross B, so it's not compressible.
Yeah, that's this approximation is isomorphic to
after
incompressible.
a lot of special treatment, it becomes compressibility for E cross B.
And wouldn't there be a non-quadratic interesting effect in plasma?
So far, we only know these two quadratic. There are, as I show here, any function of G is conserved, but only the square of the quadratic one is rugged. I can show why is it. But, yeah. And yes, and if I do the Hankel transform, I find that only two, as I show here, in the next the third version. Also, originally, if I don't do Hankel transform for velocity, I have 1 plus a continuum. Now I have 1 plus 1 because the others are not rugged. So you can show that some are rugged, some are not.
Thank you. Okay, let's move to the last topic.